Chapter 12, Section 2, Part 2 begins with Charles's Law. And with Charles's Law, it's going to compare volume to temperature when pressure is kept constant. And you'll see that volume and temperature are directly proportional with each other. So as one goes up, the other goes up as well. If one goes down, the other will go down. And our equation that we'll be using is V1 over T1 equals V2 over T2. So here's a sample problem. This one says gas in a balloon occupies 2.5 liters at 300 Kelvin. If the balloon is dipped into liquid nitrogen at 80 Kelvin, what volume will the gas in the balloon occupy at this temperature? So what we know is the first volume, we know that's 2.5 liters. We have the first temperature, which was 300 Kelvin, and we have the second temperature, which says it was 80 Kelvin. So we're solving for V2, and since our volume was, our V1 was in liters, our V2 will also be in liters, and our temperature units are both already in Kelvin, so we don't have to worry about converting those. So now we're going to write our equation, V1 over T1 equals V2 over T2. I also show it rearranged here to solve for V2. So we're going to be taking V1, multiplying it by T2, and dividing by T1. So we'll take 2.5 liters times 80 Kelvin, divide by 300 Kelvin, and our Kelvin units will cancel, and what's left over is 0.67 liters. So that makes sense because our temperature went down. Okay, our temperature decreased from 300 to 80, and so our volume should also have decreased, and we went from 2.5 to 0.67. Another equation we have is comparing pressure and temperature, similar to Charles' law, but we're flipping out volume and pressure. So this time we're keeping volume constant and using P1 over T1 equals P2 over T2. And this one is set up the same type of way. It says gas in a sealed can has a pressure of 3 atm, so that's P1 at 25 degrees Celsius, so there's T1, and adding 273 would give us 298 Kelvin. A warning says not to store the can in a place where the temperature will exceed 52 degrees Celsius, so that's T2. Again, adding 273 will give us 325 Kelvin. What would the gas pressure in the can be at 52 degrees Celsius? So we're looking for P2. Since P1 is in atms, our P2 value should also be in atms. We're writing out our equation. Again, I rearranged to show it solving for P2. So we're going to take P1, which is 3 atms, multiply it by T2, which was 325 Kelvin, and divide it by T1, which is 298 Kelvin. So our Kelvin units will cancel, and we will be able to find our volume, or excuse me, our pressure as 3.27 atms. Again, that answer makes sense. Our temperature increased, so our pressure should be increasing. And it does. It goes from 3 to 3.27. Avogadro's law compares volumes of different gases under the same conditions of temperature and pressure, and tells us that they will have the same number of molecules. One of the equations we'll be using with this is V1 over N1 equals V2 over N2, where V is volume and N is moles. The next law is Gay-Lussac's law of combining volumes, which says that when temperature and pressure are kept constant, gases are going to react in whole number volume proportions. So for instance, in this balanced equation, the proportions would be 1 volume unit of hydrogen plus 1 volume unit of chlorine would give us 2 volume units of HCl or hydrochloric acid. So we're just using the coefficients, just like we've done before with mole ratios, but this time instead of using them as moles, we're using them as volume units. Two terms to know are effusion and diffusion. Effusion refers to the motion of a gas through a small opening, such as like a puncture in your tire or something, a small hole where gas is going to get out of the tire. And then diffusion, which is where gas particles disperse from areas of high concentration to low concentration. This next law is referred to as either Graham's law of effusion or Graham's law of diffusion, either way. So what this one tells us is that at the same temperature and pressure, we can compare the rates of two gases using this equation here. And these are the same two equations. This one's just rearranged in a way that's a little bit easier to solve. And the small v that's also italicized represents the speed of effusion, so not volume here. And then the A's and the B's represent the different gases that you would be comparing. So you would simply substitute in, oxygen or hydrogen, whichever gases you were comparing. So we're going to take the speed of one gas over the speed of another is equal to the square root of the molar mass of the second gas divided by the molar mass of the first gas. So in this problem for grams, it says oxygen has an average speed of 480 meters per second at room temperature. On average, how fast is SO3 traveling at the same temperature? So we have the speed of our oxygen, which is 480 meters per second. We're trying to find out what the speed is of our SO3, so that will be in meters per second as well. And then we can also look up on the periodic table the molar mass of O2, which is 32 grams per mole, and the molar mass of SO3, which is 80.07 grams per mole. So we're going to write out our equation. And when you do this, I generally put the one that I'm trying to solve for on the top of this left side of the equation. So I want to solve for the speed of the SO3, so that's what I'm going to start with, and then put that over the speed of the O2, which means that on the right side of my equation, I'm going to have the molar mass of the O2 divided by the molar mass of the SO3. And that just makes it a little bit easier for rearranging, because then that way you only have to multiply both sides by the speed of the oxygen to get the speed of the SO3 by itself. And then we just plug in our values. So this was the speed of our oxygen, and then our molar masses, and I'm taking the square root of that, and that gives us 300 meters per second. Another way you can use the same law is with this type of problem. This one just tells us to compare the rate of effusion of water vapor with oxygen gas at the same temperature and pressure. So it doesn't actually give us an exact speed the way the previous problem did. The only thing we know here is that we're comparing oxygen and water. So we can look up each of those molar masses on the periodic table, and then what we'll do is just simply use the right side of our equation. So when you do it this way, I would put the heavier one on the top and the lighter one on the bottom. So I'm going to put the molar mass of the oxygen, because it's 32 grams per mole, and divide it by the molar mass of the water, which is 18.02 grams per mole. And then by simply taking the square root of that, I'm going to get a number value. This one comes out to 1.33, and that's going to tell me that the lighter gas will effuse 1.33 times faster than the heavier one. So water will be effusing 1.33 times faster than oxygen. And as long as you set it up this way with the heavier one over the lighter one, that will be the case.